Here's a video which is designed as a review of AP chemistry concepts that should have been picked up in first year chemistry on balancing equations and identifying reaction types, an important skill. Let's first recall the four types of chemical reactions. The easiest is simple decomposition, such as hydrated salt shakes apart, or calcium carbonate falls apart into calcium oxide and carbon dioxide, and this is usually done by simply heating the compound. There then are ion swaps reactions, and there are of two types. The first is precipitation, where an anion and a cation combine to form a not very soluble substance like barium sulfate, and the acid-base reaction, which in the easiest type you have a hydrogen compound like hydrochloric acid reacting with a hydroxide compound such as calcium hydroxide to form water and a dissolved salt. Then the largest classification of reactions would be the oxidation-reduction reactions that are extremely important in both industry and life. And there are several types of oxidation-reduction reactions. In each of those, electrons are being transferred from one compound or element to another. The combustion reaction, burning in oxygen, oxidation-reduction decomposition, such as you get when you heat chlorates and some oxides, and the redox synthesis, which is very important in biology as in oxidative phosphorylation, and of course ion and element oxidation number changes, such as happens when you mix two ionic compounds and one is oxidized and the other is reduced. Now, just to be sure, what is going to become what in an oxidation-reduction combustion reaction? And we need to look at each element in turn. In a complete combustion, every elemental species oxidizes to its highest oxidation state. So, for instance, carbon goes to CO2, where carbon is +4. Hydrogen goes to H2O, where hydrogen is +1. Nitrogen goes to NO2, where nitrogen is +4. Phosphorus to phosphorus pentoxide, P2O5. Sulfur to sulfur dioxide. And the metals, if they are burned, go to their highest oxide. So, for instance, copper will react with oxygen to form +2 copper. Halides are an exception. The halides, if for instance you've got methyl chloride and you burn that in oxygen, the chlorine does not react with the oxygen. The chlorine pairs up with one of the hydrogens in the compound and forms, for instance, HCl or HBr. Now, there are incomplete combustions, and in those you do not take the elements to their highest oxidation state, and you'll be told what the products should be. For instance, an incomplete combustion of a hydrocarbon, then you'd probably get carbon monoxide and water vapor instead of carbon dioxide. Now let's go over balancing by the inspection method. Just looking at and going left to right to balance the number of atoms on each side. The first thing you want to do is check for diatomic molecules, those things that come in packages of 2. For instance, bromine, chlorine, hydrogen, oxygen, fluorine. We use the Brinkelhoff mnemonic to remind us of those elements. They have to be shown with a subscript of 2 if they're an element. Then you balance the metals, you balance the nonmetals, you balance oxygen left and right, and finally you balance the hydrogen left and right, so that the right number of atoms are on each side. Then you recount all the atoms left and right, and you balance the equation by changing coefficients, the number in front of the compound or element formula. You never ever change a subscript in a formula once you have the proper composition. If the atoms are not balanced at this point, you need to go back to the previous slide and check each one of the elements systematically. Work your way back up the steps until you find the problem. So see if the hydrogens are wrong, then the oxygens, and so forth. If every coefficient reduces, say, by dividing it by 2, then you rewrite the equation in the simplest whole number ratio. So if your coefficients are 2, 4, 2, and 6, you would divide all of those by 2 to get the simplest whole number ratio. An equation is not properly balanced until it's written in the lowest whole number ratio of elements and compounds in the equation. Now, I would encourage you to maybe copy this on your notebook and balance these equations using the inspection method. Turn off the video player just now so you can do that. And then once you've balanced them, come back and look at the answers on the next page. So here are your answers. So for instance, we would read 2 moles of sodium hydroxide become 1 mole of sodium oxide and 1 mole of water. 4 moles of iron react with 3 moles of oxygen to form 2 moles of the iron 3+ oxide. And you can look all of these over and see how to balance them and check any wrong answers that you may have. Now we have several pages here that you can, just as before, stop each page, balance the equation. I did not provide you any solutions to those. You may want to do this with a partner or two. And I have also on each one of these given you the type of reaction that we're working with. So let's start. This first reaction between calcium and aluminum chloride, you'll see, for instance, if you heat solid calcium with solid aluminum chloride, and of course water has to be kept away from it, you'll get calcium chloride and aluminum metal. Now let's look at the type. This is a redox reaction. All elements have an oxidation number of 0. So the calcium on the left and the aluminum on the right have an oxidation number of 0. But here, since chloride is -1, the aluminum is +3, and here the calcium then must be +2 to balance off the 2 chlorides. So this is an oxidation reduction. In this next one, this is what we would call a simple composition. Here, the potassium stays +1 on both sides. The oxygen in hydroxide is -2, just like it usually is in a compound, and the hydrogen being +1. So you have +1 potassium here, +1 potassium there, -2 oxygen here in these 2 oxides on the left, and -2 oxygen on the oxide on the right. So this is not an oxidation reduction. It is just the opposite of a simple decomposition. In this one, you have carbon, which of course is an element and therefore 0, carbon becoming carbon +4. And so that's obviously going to be a change. Here, the hydrogen starts off as +1 because it's in water, and it ends up as a 0 because it's an element. Here, the equation is an oxidation reduction. If you look here, oxygen is always -2. There's 2 of them. So to balance that off, the chlorine has to be a +4 to balance off the -4 on the oxygens. And over here you see the chlorine in the acid is now a +3 here, and in this other acid it's +5. Remember, we would take the oxygens, there's 3 times -2 here on the oxide, and then we would eliminate one of the negative charges with the positive charge from the hydrogen here, and as a result the chlorine here has to be a +5. So we've gone from +4 to +3 and +5. This is an oxidation reduction. Here the 2 elements on the left are combined into a compound. Yes, it is a noble gas compound. It does exist. It's stable at very, very low temperatures, well below the freezing point of water. Here we have another oxidation reduction, and it in addition is a combustion. All combustions are oxidation reduction, and you see the oxygen here is at 0 as an element, and here it is its usual -2 as it is in compounds. This is a burning of an alcohol, ethyl alcohol or ethanol, in oxygen, and the carbon in the oxygen in the alcohol becomes the carbon +4. That's a change, and the oxygen in the elemental oxygen, as it did before, becomes the -2 in these two oxides. You can also see here two elements with zeros turn into ammonia. That is an oxidation reduction as well. And the same thing happens when nitrogen and oxygen react to form dinitrogen monoxide. Finally, we have the aluminum hydroxide reacting with sulfuric acid. It's an ion swap. You can check the oxidation numbers and see aluminum's +3 on both sides, and so that's not an oxidation reduction. And you can also see that the hydroxide on the aluminum hydroxide has reacted with the hydrogen on the sulfuric acid to make water. This is an acid-base, typical ion swap reaction.